Hey, good day. In this video, you're going to learn about work, energy, and power sample calculation. By the way, I'm Engineer Joe Masaway. Do not forget to like this video and subscribe my channel. So let's proceed. An object is horizontally dragged across the surface by 100 Newton force acting parallel to the surface. Find out the amount of work done by the force in moving the object through a distance of 8 meters. So we are given with the following parameters as your D. This is your distance of displacement as 8 meters. And then we have your parameter 100 newtons here as your force. So we are required to determine the unknown work. So let's proceed with the solution. Since F and D are in the same direction, your theta here would be equal to 0 degrees. Okay, so theta here is the angle of the force to the direction of movement. Okay, so why is it 0? Because your force and displacement are in the same direction, which is horizontal. So to calculate the work now, this gives us force multiply it with cosine theta times the distance. If we're going to plug in the values, this gives us your work is equal to 100 newtons, multiply it with 8 meters times cosine of theta, or your work would be equal to 800 joules. For your second example, what are the work and power output values for a 60-kilogram woman who runs up a 3-meter high flight of stairs in 3.5 seconds, starting from the rest, but having a final speed of 2 meters per second? Okay, so we are given with the following parameters as your mass, 60 kilograms. The height of the staircase or height of flight, h, would be equal to 3 meters. And then we have the whole duration of work as 3.50 seconds. And then starting from rest, v sub o would be equal to 0 meters per second. And the final speed or final velocity as 2 meters per second. So we are required to determine the power. This type of work power problems involving velocity and a certain height flight, you are going to consider calculating work from the sum of kinetic potential energy. Again, for this type of problems, you're going to consider the sum of work as the sum of kinetic and potential energies. Okay, so work total would be equal to KE or kinetic energy plus potential energy. If we're going to further expand the formulas, work total or total work would be equal to half of mass multiply it with final velocity squared minus initial velocity squared plus mass times gravitational acceleration multiplied with your height. Plugging in the values gives us half of 60 kilograms. And then we have this quantity. So half of 60 kilograms times 2 meters per second quantity squared minus 0 since at rest squared plus 60 kilograms multiply it with 9.8 meters per second squared times the height of the flight at 3 meters. So simplifying the whole quantity gives us 1,884 joules. Okay? Thus, the power is calculated as work all over time. So 1,884 joules all over 3.5 seconds. This gives us 538.28 or 0.29 watts. Okay. Your third example, a 5-kilogram block is moved up a 30-degree incline by a force of 15 newtons parallel to the incline. The coefficient of kinetic friction between the block and the incline is 0.25. How much work is done by the 15 newtons force in moving the block at a distance of 10 meters? Okay, so your displacement is 10 meters. So the second one, what is the total work done on the block over the same distance? So we are given with the following parameters. Your 5 kilograms here is your mass, and the angle of inclination is 30 degrees. And then the force applied to push the block is 15 newtons. Okay? And then the coefficient of friction here, mu, is denoted as 0.25. And then we have your distance or displacement as 10 meters. Now, if you're going to illustrate the free body diagram, okay, this gives us the following. We have an inclined plane at 30 degrees. Okay? So we're going to consider a block here with mass mg or weight of mg. Okay? If we are given with the following configuration, inclined plane, we're going to consider the analysis of x-axis, okay, with respect to the incline. Okay, so this is your inclined x-axis, okay, as denoted in this one. And then your y-axis would be perpendicular to your inclined x-axis, okay? So we have your forces for your x-axis as your friction, the inclined x-axis weight component, okay? And then we have your force applied at 15 newtons. So for vertical forces or vertical inclined forces, we have your normal force and the vertical or inclined vertical component force of your weight here, okay? So if this is 30 degrees, the angle here, okay, where my cursor of the mouse points at, okay, this is also 30 degrees. Now, the whole displacement for this problem is denoted as 10 meters, okay? From point here to here is 10 meters. So if we're going to proceed with this solution, okay, your solution now, the total work done for this block, okay, it would be respect to the summation of forces with forces at the inclined x-axis and then multiply it with the distance. Okay. Finding the total work done on the block is more complex. The first step is to find the net force acting upon the block. To do so, we draw a free body diagram as shown above. Okay, the free body diagram was explained earlier. For this type of problem, the next step is to determine the individual forces along the inclined axis or inclined x-axis as shown. Okay, so your inclined x-axis is here. Okay, namely the x component of the weight of the block. Okay, so this is the x component of the weight of the block, the frictional force Fk. So Fk is equal to the um, coefficient of friction, multiply it with the normal force. And then we have the force applied here as 50 newtons. Okay? So X component weight of the block is calculated as FW x mg sine of 30 degrees. So this is equal to 5 kilograms multiplied with 9.8 meters per second squared. And then sine 30 is equal to 0.5. So simplifying the whole quantity, this gives us 24.5 newtons. Normal force is always equal to the y component of the weight of the block. Thus, to calculate now your normal force, Fn, as stated on this one, Fn is equal to mg cosine 30, as you can see on the FBD. Okay, plugging in the values, this gives us 5 kilograms times 9.8 meters per second squared times cosine 30 degrees. Okay, finalizing your final force at 42.4 newtons. Then solve the frictional force Fk. How are you going to do that? To solve now for your frictional force Fk, okay, this is mu multiply it with Fn. Okay, so we have your frictional force here equal to the product of your coefficient of friction times your normal force. So plugging in the values now, 0.25 times 42.4 newtons. So where did you get that 42.4 newtons? This is the value of your normal force. Okay, simplifying now the whole quantity, this gives us 10.6 newtons for your frictional force. Now, to determine the summation of forces in inclined x-axis, okay? So if we're going to analyze your x-axis, forces towards your right. Say, for example, we have your 50 newtons. This is towards your right, okay? This is positive. Your friction would be negative or minus, and then the mg sine 30 here, or the inclined x component of your weight here, would be minus as well. So if we're going to further simplify the whole equation, summation of f of x or summation of forces with respect to the inclined x-axis is equal to negative Fk, negative frictional force, minus the x component of your weight plus the force applied. If we're going to substitute the values or plug in the values, this gives us negative 10.6 newtons minus 24.5 newtons plus 50 newtons. Or finalizing your answer into 14.9 newtons for the summation of forces with respect to the inclined x-axis. Now, to solve for the total work, okay, work now is equal to summation of forces with respect to the inclined x-axis, multiply it with the displacement, okay? So substituting the values, this gives us 14.9 newtons times 10 meters or 149 joules as your final answer for this problem. Okay, we have your fourth example, an elevator carrying four persons with a total mass of 1,750 kilograms, including the mass of elevator is lifted up at 0.85 meters per second to the 46th floor. The height of that is 180 meters high from the ground. Now, we're going to calculate the following. First, tension. Second, kinetic energy. Third, potential energy, and then the fourth one would be the work. So we are given with the following parameters, okay? So since the elevator came from the ground, at rest, that is 0 meters per second for the initial velocity, and then the final velocity will be 0.85 meters per second. Now the height would be equal to 180 meters, okay? So the total mass of both elevators and the four persons is equal to 1,750 kilograms. If we're going to further proceed with our solution, okay, for the tension exerted on the cable would be equal to the weight of the elevator and the four person, which is calculated as W is equal to mass times gravity, or 1,750 kilograms times 9.8 meters per second squared, simplifying the whole term as 17,100 15 newtons. And then for the second one, we have your kinetic energy, KE. This is equal to the half of your mass times this quantity, okay? The change of the squares of your velocity as VF squared, or final velocity squared minus initial velocity squared. So if we're going to substitute the values, this gives us half of 1,750 kilograms times the following quantity, okay? 0.85 meters per second quantity squared minus 0. Why is this 0? Because the initial velocity is at rest. Okay? So simplifying your kinetic energy gives us 632.2 joules for this problem. And then for the potential energy, this gives us mass times gravity times your height, 1,750 kilograms, multiply it with 9.8 meters per second squared times the height at 180 meters. So this gives us 3.087 millions of joules. Okay, that's a huge amount of potential energy. And then we have the last one as your work. So you're just going to sum up the kinetic energy and potential energy, okay, as 632.2 joules plus 3.087 millions of joules. This gives us 3,087,632.2 joules for your total work for this problem. So we have the last problem as your fluid mechanics problem. So this is a fluid mechanics problem or a complex problem for work energy power. So this is more on the um, this is more on the side of mechanical engineering and chemical engineering on processes which involves pumps. Okay. So let's proceed with the statement of the problem. Water with a density of 1,000 kilograms per cubic meter from a non-elevated open reservoir. When we say non-elevated reservoir, your initial height here is 0. So we are given with the initial pressure value as 0 bars for the open reservoir. Take note, okay, for an open reservoir, the pressure is always 0, okay? Flows before the pump at your initial velocity at 1.5 meters per second. The pump or the water is pumped at a rate of, this is your final velocity as 30 meters per second to a 20-meter elevated tank. Okay, your 20-meter elevated tank here is your second height. Okay, with the pressure reading or P sub 2 as 1.02 bars, assuming zero frictional losses. Okay, calculate the actual work if the pump's efficiency is just 69% or 0.69 in decimal, and then calculate the theoretical and actual power in HP for a mass of 100 kilogram and a time of 1 minute of water flow. Okay. We are given also with the following conversions. We have 1 horsepower is equal to 746 watts. 1 bar is equal to 100,000 pascals. So to proceed with this solution, we need to illustrate the free body diagram, FBD, for this fluid mechanics problem. Okay? We are given with an open reservoir. It is stated that the open reservoir has no elevation, so your H1 or initial height is equal to 0 meters. The initial pressure here in the system at the state 1, if we're going to consider state 1, this is actually the, your pump divides the system into two. We have your state 1 and state 2. For the state 1, we are given with the reservoir with no elevation. So your H1 here is 0 meters and the initial pressure here is 0 bars. We are also given with the water flow prior the pump at 1.5 meters per second. So what else? So let's proceed with the state 2. For the second state, this is the system after the pump. Okay. So we have the water flowing after the pump. Okay, so it speeds up at your final velocity or V2 as 30 meters per second. The elevation of your tank here, H2, is equal to 20 meters. Okay, so the pressure on your tank or P sub 2 or final pressure is equal to 1.02 bars. The efficiency of the pump is equal to 69% or 0.69 in decimal. And then the mass of the water flow at a time of 1 minute is given as 100 kilograms. Okay, so let's proceed now with the solution. We are required to determine the theoretical and actual power of the pump in horsepower. Okay. So to further explain this type of problems, this is actually an a what do you call this? An application of your calculus. Okay. We have your Bernoulli equation, so this is applicable for systems. Okay. Fluid flow systems. We have your water, air, and etc. Okay. On this type of problem, if I'm going to further explain this, this is already the equation, okay, simplified equation for the Bernoulli equation, okay? Instead of doing calculus here, so this is the simplified version or simplified calculus version of your Bernoulli equation, okay? Your W prime would be equal to this quantity, delta P or delta pressure all over rho plus change in kinetic energy plus change in potential energy plus summation of frictional losses. Okay, your delta F, your sigma F here is actually summation of frictional losses. Okay, to calculate now the efficiency of your pump here, your N, okay, this is actually the work efficiency for your pump is equal to your W prime or theoretical work all over W actual work. Okay. This quantity here, delta P all over rho or change in pressure all over the density of the fluid is actually your fluid head. Okay. And then as stated earlier, sigma F here or summation of F denotes summation of frictional losses for the pipes, skin friction, and etc. Let's proceed with the solution. Okay? Summation of frictional losses stated on the problem is equal to 0. Your fluid head now would be equal to delta PL over rho, or P sub 2 minus P sub 1 multiply the quantity with the mass all over the density. So 1.02 minus 0 bars, multiply it with the following conversion. Okay, 1 bar is equal to 100,000 of Pascal, and 1 Pascal is equal to 1 Newton per meter squared. This is for unit consistency to get Newton meter or Joule. Okay, and then the following numerator quantity would be multiply it with 100 kilograms all over the given density of your water at 1,000 kilogram per cubic meter. Okay, usually your water is equal to 8,000 of kilogram per meter cube or cubic meter for its density at 4 degrees Celsius up to 25 degrees Celsius. You may use this value. Okay. For your fluid head, this gives us 10,200 Newton meter per joules. Now let's proceed with the change in potential energy. Your delta PE now could be calculated as mass times gravity times change in height all over gravitational constant. If we're going to substitute now the values, we have your mass at 100 kilograms times 9.8 meters per second squared times 20, okay, minus 0. So where did we get your 20 here? Your 20 meters is the elevation of your tank with respect to the horizontal of the analysis, okay? And your 0 here is from your open reservoir with a height of 0 meters, or an elevation of 0 meters, or no elevation at all over your gravitational constant here, GC, at 1 kilogram meter per Newton second squared. So what is the use of your gravitational constant here? This is to be used so that we have unit consistencies, okay? This is for SI, 1 kilogram meter per Newton second squared. For FPS or English units, this is equal to 32.2 pound feet per pound for second squared, okay? But since in this problem, it is in SI units, so the change now in potential energy is equal to 19,600 Newton meter or joules. Now let's proceed with the change in kinetic energy. So this is in delta KE is equal to mass times, okay, this is correction, okay, V2 squared minus V1 squared all over twice of your gravitational constant. So if we're going to plug in the values, this gives us 100 kilograms times 30 meter per second quantity squared minus 1.5 meter per second quantity squared. Okay, so we have to simplify this quantity before multiplying it with the mass at 100 kilograms, and then divide the whole numerator with twice of your GC at 1 kilogram meter per Newton second squared. This gives us 44,887.5 Newton meter, or in joules. Now, to get your theoretical pump work, W prime, okay, we're just going to add your fluid head, change in potential energy, change in kinetic energy, and the summation of frictional losses. So plugging in the values, this gives us 19,600 joules for your fluid head plus 44,887.5 joules for your kinetic energy plus this must be 19,600 Newton meter per second. Although your answer is already corrected here at 74,687.5 joules. To further simplify the whole answer, okay, we're going to solve now for the actual work of the pump, or W actual would be equal to your theoretical pump work W prime all over the efficiency of your pump. Okay, so 74,687.5 joules all over the efficiency of the pump at 0.69. Okay, further simplifying the whole answer gives us 108,243 joules. To solve now for the actual power, okay, substitute the values we got from your actual work for the pump as 108,242.7536 joules per 60 seconds. Multiply it with the following conversion at 1 watt is equal to 1 joule per second. Multiply it with 1 horsepower would be equal to 746 watts or 1 horsepower all over 746 watts. Further simplifying the whole quantity gives us your final answer for the actual work of the pump or actual power of the pump at 2.42 horsepower. Okay? That concludes my presentation for the sample calculations for your work energy power. For further questions, you may message me through our messenger or FB app's messenger, or you may message me through our LMS inbox. So that concludes again this presentation. Thank you for listening. Have a nice day.